In this lesson, we'll talk about proof by cases. Often when you're doing a proof, you may end up with an assumption that has the word OR in the assumption. Remember that if we have the statement P or Q being true, what it could mean is that P is true, or Q is true, or maybe even both. So in order to work with this assumption, we'll do two separate cases. We'll do one case where P is true, and then we'll do a separate case where Q is true. When we do this second case for Q being true, remember that if we have P being true, that gives us one assumption that might give some implications, but when we then say Q is true, we cannot use anything that we got in the first case when P was true, unless that information happened to not depend on the fact that P was true. Here's our first example. Let A, B, and C be sets. If A is a subset of C, and B is a subset of C, then A union B is a subset of C. Let's start off with our usual arbitrary set statement. Let A, B, and C be sets. Now we'll make the assumptions. And assume A is a subset of C, and B is a subset of C. Now what we want to show is that A union B is a subset of C. Remember, to show something's a subset, we'll pick an arbitrary element of the smaller set and show that it's in the larger set. Let X be an element of A union B. Now, what does it mean to be in the union between two sets? Then, X is an element of A, or X is an element of B. Remember that whenever we have a union, that means it's in one set, or the other set, or possibly both. And that's what we mean by the term OR, right here. Now that we have an assumption for OR, what we need to do is split this into two cases. Case 1 deals with X being an element of A. This is what we'll write. Assume X is an element of A. Now remember, we're trying to show that X is an element of C. However, we have an assumption that will get us just where we want to go. Since A is a subset of C, we have X as an element of C. That's what we wanted. Since we showed what we were trying to prove, now we're done with this case. Let's continue on to case 2, which is the other part of the OR, the X being an element of B. Case 2. Assume X is an element of B. But now we have another assumption to help us. We cannot assume that X is an element of C because of what we did earlier. This doesn't help us. However, we do have the other assumption that B is a subset of C. Since B is a subset of C, we have X as an element of C. Now we've shown the conclusion in both cases, and technically we're done, but I want to write one little sentence just to tie everything together. Thus, in either case, we have X as an element of C, and again that proves the subset relationship, since we showed that X was an element of C for an arbitrary X from A union B. Here's our next example. For all X in the real numbers, if the absolute value of X is greater than 1, then X squared is greater than 1. Let's start off by picking our X. Let X be an element of R, and assume the absolute value of X is greater than 1. Now this is from college algebra as to what this means, but you might be able to reason your way through it. If the absolute value of X is greater than 1, that means that X could be greater than 1, but it also means that X could be less than negative 1. And if you think about it, that makes sense. Then, X is greater than 1, or X is less than negative 1. And these are our two cases. For case 1, let's assume that X is greater than 1. Assume X is greater than 1, and I'm trying to show that X squared is greater than 1. The usual technique here is multiply by something, so in this case I'll multiply by X. Multiplying by X, we get X squared is greater than X. But now look, X squared is greater than X, and X is greater than 1. Thus, X squared is greater than 1. Case 2. Assume x is less than -1. We'll do the same thing. Let's start out by just multiplying by x. But just as a warning, remember, when you multiply by x this time, x is a negative number. Multiplying by x, we get x squared is greater than -x. Now this doesn't give us an immediate link, so let's also get something for +1 by multiplying both sides by -1. Also multiplying by -1, we get -x is greater than +1. Now let's put it together. X squared is greater than -x, and -x is greater than 1. Thus, x squared is greater than 1. I could write a summary sentence this time, but we won't because it seems to make sense that for each case, I got x squared is greater than 1 as desired. This next example has a unique thing that has not come up in this lesson so far. Sometimes we have to invent cases in order to cover all the possibilities of what we're looking for. Here's our problem. Let A, B, and C be sets. Show that A minus C is a subset of A minus B union B minus C. Let's start off with our usual arbitrary sets. Let A, B, and C be sets. We want to show this subset, so let's let x be an arbitrary element of the smaller set. And let x be an element of A minus C. Now I want to show that x is an element of A minus B union B minus C. Let's at least write down what it means to be an A minus C. Then x is an element of A and x is not an element of C. That's what it means to be inside of a set minus set. Now what do we do from here? Somehow I need to show that x is in this large set here. But there's no b in my assumptions anywhere. What do I do? Well, there is one thing for certain that we can say. We don't know which one it is, but we do know that x is either an element of b or not. Note that x is an element of b or x is not an element of b. Let's use this to break it into cases. Case 1. Assume x is an element of b. Now let's look again where we're trying to go. I'm trying to show that x is an element of this large set. But just to give you an idea of what I'm going to do, remember, to show that an element's in a union, all you really need to show is that it's in at least one of the two sets. So what I'm going to do is, since x is an element of b, let's show that x is an element of just b minus c here. Now you'll notice that x is not an element of c. So what I have then is x is an element of b and x is not an element of c. That means x is an element of b minus c. Since x is not an element of c, we get x is an element of b minus c. And that's sufficient. Thus, x is an element of A minus B union B minus C. And again, the reason that this holds is because really, B minus C is a subset of the union of B minus C with something else. That's always the case, that a set is a subset of a larger set that's a union of the set with another one. I know that's a little bit wordy, but basically if you join on additional information with a union, it creates an even larger set than you had before. With that said, we can always assume that if we get x as an element of one of the two sets in a union specifically, then x is an element of the whole union. Let's do the next case. Case 2. Assume x is not an element of b. Now this time, let's show that x is an element of this set, A minus b. We know that x is an element of A, so let's use that. Since x is an element of A, we get x is an element of A minus b. And that's it. Thus, x is an element of A minus b union b minus c. And that finishes the proof since we've shown it for both cases. Here's what we got from this lesson. How do you proceed in a proof in which an assumption is P or Q? What do you think? Assume that P is true and prove the statement, then assume that Q is true and prove the statement. You're simply breaking into cases.